Hey, good morning, good afternoon, everyone. Welcome back. This is Tao Hong from UNC Charlotte. Today we have our third lecture of this distinguished lecture series offered by Professor Rob Hyndman. Today is probabilistic forecasting reconciliation. All right, Rob, please.
Thanks, Tao. Just move some things around on my screen. Okay, so let's get going. So what we're doing today is the third in this series, as Tao said, and we're going to talk about probabilistic forecast reconciliation. So just since we've all had a weekend, let's do a little bit of a recap on what we did last week. So firstly, the whole point of what we're trying to do here is to forecast a lot of time series that are related due to aggregation or linear constraints. So the example on the left is sort of one that comes up a lot in this literature, where we're trying to forecast travel, domestic travel in Australia. So the one at the top, the graph at the top, is total number of overnight trips in the whole country. And then they're split by state in the second graph, and then they're split down to regional level for one part of Australia in the bottom graph. And you can see they get noisier and noisier as you disaggregate. We're trying to forecast all of these series, and we want the forecasts to be consistent with each other. That is, that they should add up, just like the original data adds up. So forecast reconciliation involves forecasting all of the series without worrying about the constraints, and then adjusting the forecasts to make sure that they obey the constraints. And the optimal solution is known as minimum trace reconciliation, which is L2 optimal, and it involves projecting from the forecast that you obtain across all the series onto the space, which is the coherent space where everything is reconciled. So this is a linear projection. And the second lecture, we looked at lots of properties that you can derive simply because you can write this as a projection operator. And then we also looked at a lot of extensions to that, imposing other conditions like non-negativity, or we put regularization in the optimization, and so on, to get different solutions. Okay, so, and what we've done so far is only thought about point forecasts. So you're trying to forecast the mean of the future observations for each series, and the means then have to add up. So now we're going to turn our attention to probabilistic forecasting, where we're interested in the distributions being forecast, and the distributions have to be coherent. So that immediately raises the question, well, what do you mean by a coherent distribution? Because the individual draws from that distribution, are not necessarily going to add up. So we define the coherent subspace as the space on where the linear constraints hold. So this is, we did this last time. If I've got two series, A and B, and they have to add up to the total, then the data must lie on this subspace where the Y total is equal to YA plus YB. And our mean forecast must lie on that subspace too. So we describe a point forecast as coherent if it sits on that space. And our original point forecasts don't necessarily sit there, and we map them onto that space. So when we define probabilistic coherence, we have to define it in terms of this subspace in the larger space of possible values for the series. So a coherent probabilistic forecast is coherent when random draws from that distribution lie on the subspace. So we describe probabilities in terms of the usual triple, about the space and the measure. And we say that the probability triple that's coherent is related to the bottom level probability triple in such a way that the random draws lie on the subspace, and any point that's not on that subspace has zero probability. So a reconciled distribution is just a transformation of the base forecast distribution so that it becomes coherent on S. So we can think about the original base forecasts as this curly B, and the subspace that we're interested in is this section here, the red, and we're trying to project our distributions onto that space. So this is quite a new idea. Two papers have set up the definition and the theory for this. The first was a paper by Panagiotellus and 3 others, including me, which came out earlier in the year. And the second paper is by Karani, Azamonti, and Ribertu, and they did the discrete version. So our paper, the Panagiotellus paper, is how to think about this in a continuous space, and then Karani et al. Thought about how to think about it in a discrete space. The exact references are at the end of the slides. So once we sort of understand what we mean by coherent probability, we can then see what we can derive some results about it. So remember our reconciled forecasts, the point forecasts, were written like this: a summing matrix S, some kind of matrix G, which together makes up a projection. And so we can write it as S times G times Y hat. And that could also be written as S times the base. We can write it like this. And this should be a tilde, sorry. There should be a tilde. Then we can derive the density. It's a little messy, a little complicated, but we can derive the density of the bottom level reconciled distribution. And it's just a function of this G matrix, like this. So if you get the density of the incoherent, the F hats, and then we do this integration, then we end up with the density of the reconciled forecasts. That's not particularly useful as it is, because it's, this is a high dimensional integral working in very high dimensional space. So it's a little hard to work with that, but we can derive some special cases once we have the general result. So first of all, this here is for the bottom level reconciled series. So that, remember, that's a tilde. So this is for the bottom level reconciled series. To get the whole lot, we have to do this expression. Again, it's a little messy and a little hard to work with generally for any distribution, but the special cases are what's important here. So if the original series is Gaussian, then the reconciled density is Gaussian with this nice simple form. And so that's a really useful result, because often you do assume Gaussian forecasts. So that doesn't mean that the data is Gaussian. It means that the errors, your forecast errors, are Gaussian, which happens very frequently. And so that's not a bad result to have. It can extend it slightly to any elliptical distribution. So Gaussian is one special case of an elliptical distribution, and so we can also get an elliptical reconciled distribution under some pretty mild conditions. So that's cool if you're interested in probabilistic parametric forecasting, that is, you're willing to assume that the errors are Gaussian, then you can immediately write down the distribution of the reconciled forecast like that. If you're not willing to assume that the errors are Gaussian, we need to do something else, and we can do it non-parametrically. So the non-parametric approach is we have to forecast future sample paths from each of our base forecasts, each of our base forecast models for all of those different series, and then we can reconcile the sample paths. So if we take a sample from each of those base forecasts, so imagine we've got, let me just do a little diagram. So imagine we've got the total, we've got some model here, and we have, so that's for the total, and we have series A, which does something else. That's our forecast, our simulated future sample path, and we have series B, which is our future simulated sample path for that. They're not coherent, but we can reconcile them just like we can with point forecasts, and that will give us a coherent sample on the coherent subspace. So it's really simple. All you have to do is to be able to simulate sample paths from each of the models, and then you reconcile those sample paths. So the idea is you simulate future sample paths for each series, reconcile the sample paths, and then you're fine. The only thing you have to worry about here is to make sure that when you do the simulation of the sample paths, that you retain the cross correlations between them, because they're going to be correlated. And the way you do that is you have to use a multivariate bootstrap of the residuals. So rather than just taking draws from a Gaussian distribution when you're simulating the errors for those sample paths, you do a bootstrap, and rather than just bootstrapping each series separately, you have to bootstrap them simultaneously. It's not hard to do. So think about if we had 20 series, so the rows here are my series, and we've got 100 observations in our training set, and you think about this as the errors. So if you plot all the errors, what we do when we want to bootstrap from that errors, we have to bootstrap all of the series simultaneously. So we'd have to take a sample for any particular time vertically through this thing here. And so we end up with these. So this is me sampling, taking bootstrap samples of the errors. And then once we've got a set of bootstrap samples of the errors, we can then use that when we simulate future sample paths. And that's it. Like that's it. And so almost always, this is the best way to do distributional forecasting if you're not willing to make the assumption about normality. And even if you are willing to make the assumption about normality, this is actually a much easier way to get the covariance matrix. You don't have to estimate it directly. It's implicitly included because of those vertical bootstrap samples. They retain the cross correlation, so implicitly you end up with the right covariance. Okay, so that's what we mean by probabilistic coherence, and that's how you would actually do it in practice. Of course, once you've got probabilistic distributions, you then have to evaluate them, and not everyone's familiar with the evaluation of probabilistic distributions, so I wanted to talk about that. So let's do an example. So here's the Australian domestic tourism data. This is total visitors each quarter, and there's some simulated sample paths. So I'm just fitting an ARIMA distribution, and then I'm simulating future sample paths, and I do that lots of times. So there's lots and lots of them, and then I get distributions from those. So here's the deciles, for example, 10%, 20%, 30% percentiles. Okay, and there's my actual that occurred in those 2 years, and so I want to evaluate how good was my actual compared to what I predicted would happen. Now, if you're familiar with point forecast accuracy, you'll be used to taking, mean absolute errors or mean squared errors or mean absolute percentage errors or mean absolute scaled errors, things like that. But when you've got a distribution, you've got not just one number to compare it against, but all of the quantiles. So for each future value that you observe, you can compare it against the entire distribution. So let Y be the observation at a particular time in the future T, and Q be our forecast, quantile forecast for that probability. So Q sub PT means the quantile forecast at time T for a specific probability. And then I calculate this score, which gives me how good was my forecast for that probability given what actually occurred. So if you, let me just stop this for a second. Oops, I'm going to try to stop it at 0.5. That's close enough. So if you're used to mean absolute errors, that's when P equals a half, because you're trying to predict the median with a mean absolute error. And so your error is a symmetric function. But if P is say a large value, then you say you're trying to predict the 95% interval, 95% quantile, sorry, and your actual value ends up larger than that, then that's probably a bad prediction, because you shouldn't get larger values than the 95% quantile very frequently. But if it ends up smaller than that, well, that's what you would expect. Most of the time you should be smaller than that. Well, that's what you would expect. Most of the time you should be smaller than the 95% quantile. So your loss, your score is a small value. And then at the other end, if you're trying to predict something at the 10% level, you want to penalize heavily if you're under that, but not penalize heavily if you're over that. And so you do this for all of the different quantiles and you get these different shapes. So this is the shape of this quantile score function. A low value is good. We multiply by 2 here simply because that makes it more easy to interpret. It means that at 0.5, it's the same as the absolute error. And if we average over all of the possible values of P here, you end up with a measure of how good the distribution does over the whole space. And that's called a continuous rank probability score. So that for univariate forecasting, that's sort of the gold standard. It's a way of measuring the accuracy of the whole distribution and tells you whether you've done a good job. It's called a proper score because it's minimized when you get the distribution exactly right. And it both handles calibration, which is, do your prediction intervals cover the right amount of probability, and how sharp is it? That is, you want narrow intervals. So it's both of those things. It's a really nice thing to work with. So that's how you evaluate probabilistic forecasts for univariate distributions. We'll come to the multivariate one later on. But that's sort of enough theory. Let's do an example. So I'm going to look at a example that I recently written a paper on with Barman Rostami Taber. So this is on Welsh Health Board areas. So we're trying to forecast the demand for ambulance services in different parts of Wales. So Wales is divided into these regions, and the regions have hospitals, and we're trying to forecast, what's the demand for emergency services in the whole country for each region and down to the hospital level, and also for different types of causes. So we have daily data here for a few years from 2015 to 2019. It's disaggregated by the control area, which is those regions, health board, which is down to sort of small level like hospitals, the priority, is it an emergency or is it just somebody needing transport, and what type of incident was it? Was it a heart attack or an accident or something like that? So there's a lot of data here. We've got over 2 million observations, and there's 1,530 time series when you do all the disaggregations. So you can think about the country split by these three regions and then split down into 7 boards. You've got 3 different priority levels, which we call red, amber, and green, like traffic lights, and different natures of incidents, and there's quite a lot of these. So there's 1 series for the whole country, there's 3 series when you aggregate only by the control area, and so on. And if you go right down to splitting it up by control area and health board and priority and the nature of incident, which is the most disaggregated series, is 691. If you include all of the aggregations, there's 1,530 series. So this is what all of the data looks like with over 2 million rows. And we've got the region, the category, the nature, the health board, and the number of incidents. So this is the thing we're trying to forecast. That's at the top level. So this is everything's being aggregated. So that's national level. Daily numbers of incidents is about 1,000 a day. At least there is in October. If you go down to the most disaggregated level, you can see that there's lots of zeros and ones because for that particular type of incident, for that particular sort of health board area, there might not have been anything happening that day. So it's quite hard to forecast at the most disaggregated level because there's lots of zeros and ones. Let me show you some graphs. So that's a graph of total for the country, split by the 3 areas, split by health board, split by priority level, and then all of the different natures of incidents, which gets a bit messy to see. So let's pick out 4 of them so you can see a little more clearly what the shapes of things look like. And you can see that some things are seasonal, like these breathing ones, It's driven by the weather to some extent, and other things tend not to have any seasonality, like abdominal pain. And I'm not even showing you the most disaggregated data because they'd all be zeros and ones and you wouldn't see much. This is showing for all 1,530 series, the strength of seasonality and the strength of trend. So you can see that there's some series which are pretty strongly seasonal, like these ones up here. And there's some series which are pretty strongly trended, like these ones. But most of them have not much trend and not much seasonality. They're all sitting down here. We're going to need different models, but to be able to cope with those types of features. So we tried 5 different models. Now these, remember, we're doing probabilistic forecasting, so they need to be probabilistic models. So the first one, we wanted something that's naive, so it doesn't have, it's a very simple model. So we chose to use just the empirical distribution of past daily attended incidents. So just take all of the data that we've seen, form the empirical distribution of that, and that's our naive model. Then we have ETS, which of course is probabilistic because there's prediction intervals and there's distributions attached to it. Then we tried a couple of GLM type models, Poisson models. So we're assuming things are Poisson, but the mean changes with the time time since the beginning of the data. So it gives us a trend that was smooth. So we used a spline. What day of the week is it? And what time of year is it? So with the time of year, we handle with Fourier terms. Is it a public holiday or not? Is it a school holiday? Is it Christmas Day? Is it New Year's Day? So these are all predictors in a Poisson regression. And then we did a variation on that, but allowing for some autocorrelation. So that's called time series time series GLM. So exactly the same covariates, but we added in 3 lagged response values as well to cope with some of the serial correlation. And then lastly, we just did a mixture of these 4 distributions. So we just took all 4 distributions and mixed them together to form a mixture. And this is done by simulation. So you simulate sample paths from these things, and then you just grab those simulated sample paths and throw them all into one mix. So the naive is like that. The ETS we're assuming is normal. So it's like that. The GLM is Poisson, where the X is a vector of covariance, as I said. And so here's the GLM, just so you can see what things come out to be significant, pretty well everything. So there's strong, these splines are the time trend. This is the day of week, where Sunday is the reference category. There's a Fourier term, so they're significant. There's a time of year effect. This is on the total, the annual whole for the whole country. This is public holiday effect, school holiday effect, Christmas effect, New Year's Day effect. So everything's significant. We've got a lot of data, so that's not too surprising. They don't have to be big effects to be significant. And then the time series GLM looks quite similar, except that you've got these extra terms here to cope with the correlation. Now, we're trying to do this in a Poisson framework, so you need an exponential here. And so we wanted to take the log to keep it on the same scale, but you can't take the log when you've got 0, so we're using the log of the data plus 1 to put in the covariate of response. So the idea, and then we want to do a bootstrap reconciliation. So we fit models to all the series, we store their residuals. So they should be serially uncorrelated because the models are supposed to deal with that. If it's a bad model, it won't necessarily be serially uncorrelated, but the good ones will. And then, but they will be cross-sectionally correlated because, the total for the country is going to be correlated with the zones, and the zones are going to be correlated with the, more disaggregated data. So we need to preserve that cross-sectional correlation by doing my vertical bootstrap trick. Then we simulate sample paths using those draws from the residuals, reconcile them using minimum trace, and then combine them, the reconciled sample paths, to form a mixture distribution at each horizon. So we're going to evaluate this using a rolling origin, so 10-fold time series cross validation. So each training set will consist of some data up until a certain point, and then we're going to be interested in forecasting 84 days ahead. 84 is important because the planning horizon for the ambulance board is between 43 days and 84 days. So they don't change the schedule for the next 6 weeks. They are planning for the following 6 weeks. So we need to think about how good are our forecasts, not 1 or 2 days ahead, because it's too late then. They've already set the schedule up for all of the staff. We want the forecast from 43 to 84 days ahead so that it can actually affect planning. So we do these, so this shows the next 6 weeks ahead and then the following 6 weeks ahead. And it's the darker orange is what we care about. We're going to have a look at point forecast evaluation. So we'll use MACE, the mean absolute scaled error, like that. And we'll do mean squared scaled error, like that. And we'll do CRPS, which is what I was explaining before, the continuous rank probability score, which I expressed last time as an average of quantile scores, but you can also express it like this, as the squared difference between two distributions. They're equivalent. So I'm going to take my CRPS as the mean of these guys, where the G is the distribution for whatever method I'm looking at, and F is the true distribution coming from the actual values. And I'll need to scale this so that I can make comparisons. So I'm going to scale it by looking at this relative to what I got for the naive version. So this is the results for the 5 methods, the 4 plus the ensemble. And you can see, just take the point forecast to start with, the mean absolute scale error, the darker orange, that's naive. So that's the worst everywhere, which is not surprising. It was a very simple model. And the best is this yellow one, which is the ensemble, which is not surprising again, because combination forecasts generally do better than the components. The CRPS, which is the new thing here, the naive is of course 1 everywhere because it's relative to naive, so it has to be 1. And all of the others are better than naive. And again, the ensemble tends to be a little better than the others. Not always, but mostly. So this was from a weekly level up to 12 weeks ahead. We're really interested in week 7 to 12 because that's where the planning goes. So let's just focus on that and look at the tables of the results. So here's base forecasts. So these are not coherent, so we don't want to use these. They're just put in there for comparison. And here's my MINT forecast on the bottom, down here. And you can see that the ensemble is better almost everywhere. And the naive is worst everywhere. That's mean squared scaled error, mean absolute scaled error, and CRPS. And you can see again, ensembles tend to do better everywhere. This one is slightly better, but look at the difference. It's not significant. It's almost identical. Okay, so we've got a really strong message coming out here that ensemble mixture distributions give better forecasts than any component methods, that forecast reconciliation improves accuracy. And interestingly, even when some component methods are poor, like naive was a bad method, but the ensemble, the reconciliation still works, and the ensemble without the naive was actually worse than the ensemble with the naive, which is really quite surprising in some ways. Putting in bad methods into your ensemble doesn't always make things worse. And the idea here is that forecast reconciliation allows coordinated planning and resource allocation, because you need to think about the distribution of demand at different levels in the system. Okay, so that's a relatively simple example where we were just interested in how good were our forecasts for each series and then averaging across them all. But remember, what we're doing here is actually multivariate. We're forecasting lots of different series, and that forms a multivariate distribution. So we probably should be thinking about how to evaluate it across the whole lot. So that leads me to discuss how do you do evaluation of multivariate probabilistic forecasts. So let's write down again another way to write down continuous rank probability score. So when I first introduced it, I used this idea that it's an average of quantile scores. But you can also express it like this. It's equivalent, where it's the difference between these two expectations, where y is your is a draw from the true distribution. Y sub t is what you actually saw, your observation. And y star is another draw from your, not from the true distribution, from the forecast distribution, sorry. So this is from the forecast distribution, and these two are draws from the forecast distribution, and this guy is the actual. So it's, if your distribution is good, then these things should be small. If your distribution is not so good, then then this part at least will be large. And it's optimal when you've got it right, when F is the true distribution, then you call it a proper score. Okay, so that's CRPS. But what we can do is we can take this and say, well, that, because it's just expectations, we can do the same sort of thing with multivariate forecasts. So, and we call that an energy score. So it's a natural extension, a natural generalization of continuous rank probability score, where it's just take the same expectations, but they're now vectors rather than scalars. So that's one way to do probabilistic multivariate evaluations. There's another way, which is in some ways a little more popular, I think, which is simply to take minus the log of the density. That has this really nice sort of easy thing to think about, nicely interpretable, because the density, your predicted density should be high where the actuals occur. Like if you've got a good predicted density, then the actual should be somewhere near the center of it. If you've got a bad predicted density, then your actuals might lie in the tails. So the value of your density at where you're at the observation should be a large number. If you've got a good distribution, minus the log of that should be a small number if you've got a good distribution. So that's sort of nice and interpretable. Unfortunately, it has some problems when we try to use it in this context, which I'll explain. So ideally, we want to use a proper score, which is optimized when you get it right, when somehow or other your model actually is the truth. That, of course, never happens, but you want a score that has that nice property. And it turns out that if you're trying to compare a coherent distribution with an incoherent distribution, the log score is not going to be a proper way to do it. And it's not hard to see why, because remember, if it's incoherent, then you've got zero probability off the coherent subspace. So this F will be zero when you've got incoherence, and then you've taken log of zeros, and that's going to give you problems. So the log score is not proper for this comparison, whereas the energy score still works. If you're comparing one type of coherent distribution with another, then they both work okay. But you do have to be careful that you use all of the series. So the full hierarchy should be used, otherwise you're going to get different orderings going on. So the ordering is preserved if you compare using only bottom up, and therefore you need to use the full hierarchy. Okay, so we're going to use it for these reasons. We're going to have to use energy score because it's the only proper one when we've got doing this comparison. And so in this paper by Panagiotoulis, we proposed optimizing G, because there's no reason MINT should be the best. MINT was the best for mean squared error, but there's no reason MINT's the best for everything else. So the idea was, well, what is the best forecast for optimizing energy score? So compute OLS, start with an OLS because that's easy, and then we'll iteratively update it using stochastic gradient descent. So SGD is stochastic gradient descent, and see if we can find the best G. It's a bit slow because it's a big matrix, but this is the idea. So let's see how that works in practice. I'm going to use a different example. So this is forecasting daily time series from Australian electricity generation. So electricity is generated. We have the total generation for the whole country. We have generation from renewables and non-renewables. We have generation from gas, from distillate, from coal. Coal can be split into generation from black coal or brown coal, and so on. And we're interested in all of these things. Can we forecast all of this? So there's 23 series here in total, 15 at the bottom level, and then all of the others make up different aggregations. Here is the total generation for the country. There's wind generation, there's solar generation. This is just over the period between June 2019 and so it's about 1 year of data up to May 2019. So, you know, solar goes up in summer. Summer, of course, is around December, January in Australia. This is distillate production. So we're going to do another rolling window approach. We have a rolling window of 140 days of training data, and then forecast for one step ahead for 170 days of test data without refitting the model. So just one step ahead, and then we just roll this thing forward. We have using a neural net with up to 28 days of the target variable as input. So just autoregression, but a neural network autoregression. So the net R function in Fable will do this. I'm not saying it's the best model. If we had a temperature in the model, it would be better because temperature is a good prediction of electricity demand, and generation is driven by demand. Now, if you know it's going to be high demand, then you generate more electricity. But for the sake of this exercise, we're not going to put in temperature. So here's the residuals for the different series, and you know, they're clearly non-Gaussian. You get this, for example, this one here. You got this really big tail like this, and even some of the others, they almost look like this. This sort of looks bimodal. So we don't want to assume Gaussianity here, but we can use bootstrapping again. This is the residuals, and you can see that they are quite correlated in not very surprising ways. So here's total for solar, and here is rooftop solar. And so obviously rooftop solar is part of total solar, and so they're going to be strongly positively correlated. So a big circle is strong correlation, and blue is positive. Big negative is this one. So that's gas production using steam and wind. So they tend to be negatively correlated, probably because gas is being used as a substitute when wind is not available. So if you're not generating enough power from your renewables, then you bring in some of the non-renewables. So there's sort of cannibalization happening here, which causes negative correlations. So let's do this. We'll do forecasting, and we'll try different things. We'll try assuming everything's Gaussian and ignore the cross correlations. Everything's Gaussian, but we'll build in the cross correlations, and then non-Gaussian, ignore the cross correlations, and non-Gaussian with them. So the non-Gaussian dependent is what I described using the bootstrap method. And we'll do just the original forecasts, just taking the bottom level and aggregating them, and then a few different methods, which I haven't talked about. This one from a paper I wrote with Sohaib Ben Taib and James Taylor, which appeared in JASA. It was actually the very first paper that described probabilistic reconciliation. It's not as good as the later stuff, but it was the first. This one, can't remember where it appeared, but again, a very early paper on probabilistic reconciliation, and then we'll just use ordinary least squares, mint, and to do the form the G matrix. And then the last one is where we'll do the optimal G using the stochastic gradient descent idea. So here we are. So we've got all these different things. So we've got for each of these four, we're applying each of these guys. And they're all shown in the graph. So this is mean energy score, small is good. So you can see that the green one, that's JPP, and the light blue one is BTTH. So these first methods, these two are worse than everything else. But remember, these were the first attempts to do probabilistic reconciliation. And we've learned from them, and we can now do it better. The next lot are all using this idea of reconciliation that I described, where you take this G matrix and you project the distributions. Well, the base is not doing that. Base is the original forecasts. Bottom up is taking the bottom forecasts and then just summing them. And then these three are using the three different methods: OLS, mint shrink, and score optimization. So you can see that score optimization is actually working really well, even when you make these bad assumptions that everything's independent and Gaussian, which is not true. You still do well. And if you do it using the correct assumptions, it's about the same. So it's not very sensitive to that. But the other methods, the mint, shrink, and OLS, they tend not to do well if you make bad assumptions. But once you take into account you're either doing bootstrapping, so you're getting the distribution right, and allowing for the correlations, you're doing much better. Are they actually different from each other? So let's look at where things are different. So you can see this is these Nemini diagrams, which if you've read some of the literature, you've probably seen these before, where you're looking to see what's correlated with what, and the black and the blue are showing you which ones are similar or different from each other. Okay, so let's stop there for some questions. I just wanted to point out where all this stuff appears. So the two papers that I said were the earliest ones to discuss this were these two. The one by Gion Panagiotoulis and Petropoulos appeared in EJOR, and then the one by Ben Tayeb, Taylor, and me appeared in JASA. So that was sort of the early approaches to doing this. And then more recently, when we figured out how to do it better, is the theory parts of it are in these two papers. The IJF one has not actually yet appeared. It's appearing in a special issue of the IJF on hierarchical, on forecast reconciliation. I mean, it's online. You can read it, but it's not yet officially allocated to a journal because we're just putting the final touches on that special issue. And this other one was in EJOR. So they describe more rigorously what we mean by probabilistic reconciliation, and this one does the optimal G approach. And then the last paper, which has not yet been accepted, but we're close. We're in I think the third round of revisions. That's the application that I just described using the Welsh Ambulance Board data. Okay, so we've got plenty of time for questions today, so we'll stop there.
All right, I typed something in the chat while you were showing the results of your the GLM, I think it was, where you sort of started thinking about significance, and I was surprised to see Saturday wasn't significant, but then I thought maybe it's because it's very similar to Sunday, right?
Yeah, that'll be weekends are the same.
Yeah.
Yeah. Where was that? That was here.
I mean, we know that we don't care too much about significance when it comes to forecasting, but you were looking at them, so.
Yeah, that's right. So these are the day of week effects, and it's relative to Sunday. So it's basically saying that Saturdays and Sundays are pretty similar to each other. The p-value is not huge, but it's not quite significant. Yeah. Finn's got a question. In the hospital example, the reconciled forecasts of the bottom levels are much worse than the base forecast of the bottom levels. So where's that coming from? Here, right? let's do it. Distribution, the reconciled forecasts. Is that what you mean, Finn? Or this one? Oh, over here. Oh, I see. We're comparing these with these?
Finn, you can unmute and talk if you want to.
Yeah, sorry. I was referring to the point forecast, not the probabilistic forecast.
These guys. Yeah, so so they're much worse, aren't they? The bottom level forecast. So the bottom level is really just highly disaggregated, and we have made things substantially worse there, but better at the higher levels. Yeah, so I suspect here that we probably don't want to be disaggregating quite so much as we are. So yeah, nobody's really interested in the forecast for a particular level of particular type of incident with a particular board. Like no one's going to act on that information, and I suspect that that's causing problems at that bottom level. But yeah, it is curious why it does so badly in the point forecast. Not so bad on not so, that's also pretty bad, but not so bad at probabilistic level, but still a little bit worse.
I've also got a related question, if that's okay. So for the bottom level, there are lots of zeros. Is this treated sort of specifically in the forecasting model with the regresses?
Yeah, so for some of them, I'll go to the models, the list of models here. So naive is going to handle that fine because you'll just have a big spike of zeros in your distribution. ETS is ignoring it. So that's, so you will get some problems happening in your ETS model because of that. And these two are Poisson. So they're going to allow for count data, and they should be able to handle data with just on zeros and ones without too much trouble. Probably a lot of the predictors might be insignificant, and we haven't attempted to sort of pick the predictors for each individual series separately. We just use the same predictors for all the series. So that could be one reason actually why the forecasts are not so good at the bottom level too.
Yeah, thanks a lot.
Question from Leonidas: when you're doing the reconciliation with sample future paths, do you have to reconcile all sample paths individually as if they're point forecasts? Yes, that's exactly what happens. So you do a simulation, and so so the first simulation, you're simulating all the series, and then you reconcile them, and that gives you a set of a draw from the coherent space. And then you simulate all the series again, reconcile them, it gives you a second draw from the coherent space. So you don't have to change the size of the matrices. It's the same, well, at least the reconciliation matrices are exactly the same. You are storing a lot of stuff here, but you don't have to store each of the unreconciled ones and as well as the reconciled ones, because you can do it iteratively. You can just do a simulation, reconcile, and only store the reconciled ones. So it doesn't really increase the storage too much, but you are actually reconciling all the sample paths as if they're point forecasts. Marty's asking, for emergency case study, did you have lumpy data? What do you mean by lumpy data, Marty?
Marty, you can also unmute and talk if you want.
So lots of zeros and some lumpy spikes.
It's lumpy and erratic data. Just wanted to see, maybe that's the reason the bottom level is not working so well. And how would you approach forecasting that?
Yeah, so first of all, lots of zeros. Sometimes you end up with more zeros than you would get from, say, a Poisson regression. So you can do zero inflated Poisson. That's relatively straightforward to do. It's basically you fit a model for is it zero or not zero, and you fit a separate model for given that it's not zero, what's my Poisson look like? So that's called zero inflated. That's easy to cope with. if it's lumpy in other ways, so you might have sort of something that looks like Poisson, except you've got a large number of threes, for example. Sometimes that can happen just because of the way the service works. You end up with it not, certain numbers can come up more frequently than others. These models don't really handle that sort of thing very well. You'd have to try to build something more empirical. Now, obviously, this first one doesn't take into account, seasonalities or trends or public holidays or anything. But if you would have to do some kind of empirical approach that did take that into account, I can't think of how to do that off the top of my head, but that'd be the sort of the direction I'd be trying to do if you had something that was sort of lumpy, that didn't fit a nice distribution. Any other questions before we finish up?
Rob, I have a question. This is Tao. Yeah, so there was a page you mentioned that I think you were surprised too to see, I think in ensembles, even with the bad component,
Yeah,
it was producing better results. Yeah, I think it's at the end of this section, probably.
yeah. Back here. So the point we were making there was that so we put into our ensemble these 4 methods. So they're mixed together to form a mixture distribution to give us this ensemble. And you can see that the naive is really bad. Like, it's way worse than everything else. If you just look across this list here. So the natural question is, well, maybe you should be using an ensemble only based on these three, and leave out the naive. And maybe you'd get a better result. And it turns out we got a worse result by leaving out the naive. And I think what's happening is although it's a bad forecast on its own, I think it's causing some shrinkage towards the stationary distribution. So if you think about what the naive is, it's the empirical distribution of all the data. So it's a stationary distribution. It was what you would get if you had stationary data. And when we put it in the ensemble, you're forcing the ensemble distribution to shrink a little bit towards the stationary distribution, because that's one component of the 4. And I think that creates a little bit of regularization. And that seems to be the reason I think that it improves things. So, obviously, bad forecasts are not always going to improve an ensemble. You could throw something terrible in here and it's going to make things worse. But in this particular case, it didn't make things worse. It made things better. And I think it's because of that sort of idea of shrinking to the stationary distribution.
Yeah, I wonder if you try throw out one of those 3 better ones and see if it's, give you a
Yeah, we
better
didn't try that, but yeah, didn't try that. Don't know what that would do.
Because I'm thinking maybe the naive somehow offsets some of the others. Maybe the others are in like one direction and naive it's in the other direction in term.
Maybe these 2 are moderately similar. They're the same model, just one has extra covariates in it, which allows for some of the serial correlation, which is really only going to affect your short-term forecasts. And we're talking here about the long-term forecast. So these 2 should be pretty similar in the long term. And as you can see, the numbers are almost the same. ETS is a little bit different because it's ignoring the count nature of the data. And if you've got an additive ETS model, you're probably also going to have some negative values. What we were doing was, if they were negative, we just set it to 0, set the distribution to 0. So you ended up with a 0 spike plus this continuous bit. And yeah, it's possible that leaving that out might make things better. I don't know. I'd have to try it.
Rob Savandi's got a question about the ensembles, whether you're taking the mean of the forecasts.
No. So what we're doing is we're taking the mixture distribution. So all of this is probabilistic. So we get distributions from each of the methods. So we have for each of these methods, we get a distribution, and then we mix the distribution. So it's this, because they're simulated distributions, we just get a sample from these distributions. So you suppose you got a sample of 1,000 from here, and 1,000 from here, and 1,000 from here, and 1,000 from here. Well, this will just consist of 4,000 size sample. So it's just a mixture. But the mean of the mixture is equal to the mean of the means. So if we took the means of these, then this is equal to the mean of that, simply because that's how mixture distributions work. That preserves the mean of the other point forecasts.
Okay, one more from Leonidas.
Okay. Do you have any advice on bootstrapping the residuals versus one step ahead cross-validation errors? Yeah, so that's general. That's actually a question that could apply generally in forecasting, not just in this context. So residuals are cheap and easy to compute because you sort of got them anyway. Once you fitted a model, you've got the residuals. And so resampling from them is super easy and fast. Whereas if you did one step ahead cross-validation error, so you're fitting a model, predict one step ahead, grab the error, fit the model to that longer one's, the training set one step longer, do it again, and so on. If you do that, then you will get errors that are have better properties because they will not, you won't get the overfitting that you get with residuals. So your variance of those cross-validated errors will be slightly larger than the variance of the residuals. And therefore, you will end up with probably better distributional coverage. So it is better to do that, but it's just so much slower that, and the benefits don't really outweigh the advantage of the speed, because residuals are you can do almost without any extra computation. But yeah, you're quite right in your worry that the residuals can result in narrower distributions. That's true, but hopefully you're not overfitting so badly that that's the problem. I mean, it will be a problem if you're fitting really, really complicated models that are completely overfit. In this example, because we've got loads of data, 4 years of daily data, overfitting is not going to concern me, and therefore the residuals are going to be almost as good as doing your one-step cross-validated errors. Also, as you point out in your question, you sometimes can't get a big enough sample with out-of-sample errors if you don't have long series, and then residuals are going to do better than in any case. So yeah, you're quite right. It's more about speed. Okay, 10 o'clock. Why don't we stop there? So let me just go back to where we're up to. So we've done the first 3. The last thing I'm going to do in this series later in the week is to now take all of what we've just been talking about and apply it in a temporal sense as well as a cross-sectional sense. So all of our reconciliation has been, we've got multiple series and we're interested in reconciling across all of these series. What we're going to do next time is talk about in the time direction. We might only have one series and we're trying to reconcile, daily forecasts with weekly forecasts, with monthly forecasts, with annual forecasts. So that's temporal reconciliation. And then cross-temporal is both at the same time. So we'll do that next time.
All right. Thank you, Rob.
Thanks, Rob.
Okay. See you all later in the week.